I would like to invite Mr. Stephen Austin. He's the Field Operations Section Director for TxDOT. Welcome, Stephen, and his presentation title is TxDOT Load Testing Toolbox.
Good morning, everybody. Thanks for joining this morning. As Robbie mentioned, I'll be talking about TxDOT's Load Testing Toolbox, and really this is resources that we've developed over the last few years, and kind of go into a little bit of detail on what we've done with those resources. So giving a little bit of background, load testing has really historically been done to assess the bridge performance. This has been done for hundreds, if not thousands of years to evaluate, make sure that a bridge is safe to remain in service. Load testing is still done in European countries in some cases to verify the capacity of a bridge before it's opened up to service. In the United States, load testing is mainly performed on in-service bridges after they've been in service for a little while, and we're trying to maybe sharpen the pencil or take advantage of material properties to increase the live load carrying capacity of a bridge. Obviously, we're not increasing the carrying capacity of the bridge. We're just coming up with refined analysis to supplement traditional load rating calculations and to take advantage of secondary effects, some unintended components that weren't originally intended to add to the structural capacity. And then load testing is also used when the current analysis can't provide satisfactory answers to performance questions. TxDOT utilized load testing to verify in-service capacity of culverts. So this was a really useful use of load testing. Other ways that load testing can be used is to verify bridge performance, maybe after a strengthening project is complete, to verify that a structure is performing as it was intended, especially when we have new technology. So yesterday was a mention of titanium strengthening. So you might early on in the implementation of titanium strengthening, instrumentation was used to verify, hey, we're getting proper performance out of that new technology. So load testing is generally one of two types, fall usually in one of two categories. So we've got diagnostic load testing, where the test truck is less than the calculated capacity, where bridge plans exist, and we're using this testing to calibrate numerical models of the bridge. And then we've got proof load testing, where if maybe you don't have existing plans for a structure, or we're trying to see how much the structure can carry, loads are applied incrementally, and increasing loads are applied to the structure, and the response of the structure is measured through the instrumentation. As soon as you see some nonlinear response in the instrumentation or the testing, then you'd say, hey, we've kind of reached the nominal capacity of the structure. Load testing at TxDOT, we've used it more commonly and it's served as an important tool for bridge evaluation. TxDOT has historically relied on consultants to perform load testing through consultant contracts, but we've more recently initiated efforts to build our in-house capability. This has been kind of a multi-pronged approach, taking advantage of TxDOT's research program, acquiring load testing equipment and instrumentation, growing our in-house expertise by having folks involved in research and involved in getting into the weeds on consultant tasks, consultant assignments, and hiring folks that are familiar with load testing. So one example of taking advantage of our research program is a research project out of the University of Texas at San Antonio. This was Research Project 6950. The subject of it was digital image correlation. This project was intended to validate the concept and develop hardware and software to measure deflections down to 1,000th of an inch, to properly measure deflections and even strains using high resolution cameras. The total project cost was $419,432, And at the end of the project, we had implementable results and equipment that we've taken advantage of to perform load testing. There's some, so we had a laptop, data collection and processing software, some calibration equipment, a user manual, and of course the very high resolution cameras. We had to purchase some accessories, obviously, to go with the fancy equipment, like tape and power banks, measuring, just miscellaneous supplies to really outfit ourselves. Another research project is one that just recently concluded out of the Texas Transportation Institute. This was Research Project 7038. And this project was intended to evaluate and develop the equipment to measure gross vehicle weights and axle weights using bridge weigh-in-motion technology. So we're familiar with, most of you probably familiar with permanent weigh-in-motion stations, maybe even some portable weigh-in-motion stations. That's more recent in here. Expanding on that, we're instrumenting bridges, and then writing an algorithm specific to that bridge to measure the response and come to a conclusion on what the loads that bridge is seeing. So we don't have hardware or software as a result of this assignment, as a result of this research project, but we do have knowledge that we're able to pull from, and we've grown our in-house expertise through this project. So kind of a high-level summary on the results of the project is that this project demonstrated that we can pretty reliably produce the axle number and spacing, the speed of a vehicle, the gross weight of a vehicle crossing a bridge, and the classification or the type of vehicle that's crossing the bridge. There was a whole lot larger variability when it came to axle weight, so it can't as accurately predict or not predict, but determine the axle weight. Traditional instrumentation, kind of outfitting ourselves with strain measurement system, equipment, instrumentation for diagnostic load testing. We've invested about $40,000 in wireless equipment and strain gauges for instrumentation of steel and concrete bridges. And then we've in addition to the STS equipment that we purchased from BDI, we also purchased some truck weigh scales. So this gives us the flexibility to respond more quickly without the coordination with enforcement agencies that we turn to for these scales. And of course, there's a few accessories that we needed to purchase to implement that. I mentioned we're growing staff expertise. Our load rating staff and our bridge preservation staff have become more engaged in the related research and implementation of that research, and implementation of the equipment that we've purchased, that we've procured. And we're trying to engage all levels of load rating staff for redundancy. So we've got our state load rating engineer involved, as well as our two bridge load rating engineers that work real closely with him. So to kind of give a perspective in the picture, yellow hat means that they've been at TxDOT for less than a year. So we've got kind of a spectrum of folks involved. We're trying to grow excitement about this capability. I think a lot of times the excitement and energy that we get, the championing that we get from our division leadership, Graham Bettis, and the passion that he's got really passes down to the younger folks. So I think that's really been helpful to get the new folks excited about it. And again, finally, the last thing is hiring the staff with expertise in instrumentation and load testing. We were fortunate to bring on board somebody that had performed thousands of load tests on bridges here recently. So that's been a great add to our team. So one example that we had that we just wrapped up a few months ago, and we're able to remove a load posting on a bridge, was a bridge that was built in 1932 and widened in 1967, consisting of reinforced concrete T-beams. So on this bridge, we installed strain gauges across the bridge on each of the girders, and at the same time, we instrumented with our digital image correlation. If we're going to close a bridge, let's take advantage of it and compare results from our two methods. Load testing, again, we installed our strain gauges, and because it was concrete, we used the extension arms, and we took advantage of our wireless nodes. So there wasn't a whole mess of wires out there to get tangled up or to rely on. That STS equipment's actually pretty. The connections and the wireless communication equipment is pretty fancy, and if you haven't seen that, it's light years ahead of the running hundreds of feet of cables across a bridge. So we took advantage of our scales before heading to the bridge to get a head start and minimize closures at the bridge. And then we set up different load cases, different loading scenarios for the structure. At the site, we were able to review our measurements to make sure that we had linear response, that we performed the same loading configuration a couple of times to make sure that we had reproducibility of the results. And then we were able to quickly look at the results to make sure that the sensors were behaving properly, that they were returning to about zero after the load was removed. This was something that early on in our instrumentation we didn't pay as close attention to, and so we'd leave the bridge and then we're processing the data and realized, you know what, something goofed up with our data or with the load, and we got to go back. So that's been a lesson learned that I think the years of experience that we've now built up, it's been a lesson learned. So some results of the response of the structure for the different loading scenarios, strain measurements for each of the girders. And then so we use those results to, in combination with MBE Chapter 8, to really take advantage of the K-factor method to refine the load rating and remove the load posting on the structure. So kind of a little bit of details on digital image correlation. Targets are installed on a bridge, so these are markers that are picked up with the high-resolution cameras. Cameras focus on these targets, and then once we're ready, we close the bridge to traffic, load the bridge up, and then measure the response. All of that's recorded, just like it is in traditional strain instrumentation measuring, and then we process the data. And again, we're able to see the results live in the field so that we can, so we know, oh, you know what, something's off. One of the things about digital image correlation, we need to keep our cameras 40 to 110 feet from the targets, and they need to be about level with the targets as much as possible, so that the triangulation between the two cameras can pick up the really fine small displacements. So again, similar to the other, similar to traditional instrumentation, we consider different loading configurations, and you measure the deflections. So slight difference, the strain gauges that we used measured strain. This really more reliably picks up on deflections rather than strain. So using the deflections and moment of inertia for each of the respective beams, divided by the summation of the deflections and the moment of inertia for each of the respective beams, we're able to come up with a more reflective live load distribution factor of what we're seeing in the field. So we've implemented this load testing using digital image correlation on now 11 bridges, and we think it's really been a great success. Setup is pretty easy because it's gluing these markers onto the soffit of the girder, and the load test can be performed in 1 to 2 hours. That's from showing up on site, getting everything out, quickly fixing the markers, and then closing it down. So bridge closure lasts 10 to 15 minutes, which is pretty impressive, we think. We can perform a load test on 3 bridges in 1 day. We did that in one case, and we're seeing pretty reliable results. So a couple of lessons learned. Site preparation is important. We've been able to work real closely with the district maintenance offices to really clean up that area under the bridge in advance of us getting out there. So that coordination has proven to be really helpful. Plan for weather and light conditions. Shadows will throw off the results with this high resolution imaging. So trying to time it right and think ahead. Do I want to be on this side or this side? Because after about an hour and a half, I'm going to be running my load test. So where will the sun be? So that's something that we need to think about. It's been a lesson learned. Available right of way, keeping in mind that you need to be off a ways. You don't want to be so much at an angle to pick up those deflections. And then high traffic areas, obviously that's always a challenge when it comes to closing a structure for any load testing method. To kind of build on what Dick mentioned yesterday, communication, keeping that up is real important. And I think being on running, having one person run point and set up a game plan for everybody involved ahead of time and then out in the field has been a real key to the success of the implementation of load testing here. So that is pretty much the end of my presentation. There's 2 folks that are really spearheading this, Estiac Hassan and Jesus Alvarez at TxDOT leading this initiative. So, any questions?
Another question about a comment about the digital image correlation technique. There are now methods actually that's been under development for the past 10 years where you don't even need to use the target and they overcome the problems like scene clutter, shadows, all kinds of things that can corrupt your results. Just wanted to say that you might want to look into those options as well.
Thank you. Yeah, the researchers at the time that this project was kicking off, we're familiar with instrumentation. I mean, this is a technology that's been used in laboratory settings, but we weren't able to find that there had been widespread use for sure in bridge load testing.
It's kind of related to that, and the question was whether you had run these kind of tests on very wide bridges where you end up with a lot of darkness underneath, and whether that created an issue if you've run if you've made a test under a case like that.
We have, I don't think we've done a really wide bridge, but as long as there's enough light to pick up the markers, the markers, I mean, we've got lights that we can even turn on. That's probably
Again, that's what I meant.
For that.
Did you end up using artificial lighting in order to be able to?
No, we haven't needed artificial lighting. I think we've been fortunate enough that we haven't had anything too wide.
Yeah, thanks so much. It's a really interesting presentation, Stephen. Question: Have you guys seen? You noted some of the shortcomings, like in high traffic areas and things like that. So, are you able to correlate these results to other bridges in your inventory? That this bridge we just did. This is a bridge that's similar. Whatever, you can be able to just say, okay, it was there, it's here, we can do that. Is that what you're looking to do?
We've talked about doing something like that. We haven't yet. I think we probably need to do a little larger inventory before we start saying, hey, this is a pattern that we've seen on this structure type. But that's a good reminder that that's one of our goals for sure. Well, thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.